Now, in this segment, we'll look at the adapter design pattern, of which method keySet is an example. And we'll also look at another small non-gang of four design pattern, which we'll call unsupported method. Now, it would seem from our discussion so far as though keySet makes a copy of all the keys in its map, puts them into a set, and returns it. Sort of like this picture here, where we have a keys that points to a copy of the keys that came from catalog. But that is, as a matter of fact, not true. The truth is more complex, as illustrated in the alternate diagram over here. The only copy of the keys is within the map. And the keySet call returns a specialized set class whose code directly accesses the keys within the map without making a separate copy of them. For instance, when you get an iterator from keys in process orders, as we would here for the for each loop, the iterator walks directly through the catalog data. If you add a new key value pair to catalog, say down here, it shows up automatically in keys as well. Since keys has no data of its own, it's effectively a different view of catalog, a way of working with the catalog as a set of keys. This is, by the way, why I indicated in a prior segment that it was not quite correct to say that a keySet call on a hash map returns a hash set. The exact statement is that keySet returns a specialized implementation of set, which implementation addresses the underlying hash map and therefore behaves like a hash set would. Our diagram, by the way, just shows a key value array for simplicity, but in truth they'd be in a hash table or a binary tree or some other such data structure, and this would determine the behavior of the set that addresses them. So the keySet call lets us view or access a map object via a set interface. Now, it's often useful to view or adapt an existing object to match a related but somewhat different interface. And we might call a class that lets us use another class via a different interface an adapter. So keys is such an adapter. Sometimes classes like map provide their own adapters via methods like keySet. But the much more common use case for adapters is to adapt a class from an older version of the code or a class from a third-party library to work with a new interface. Here's a typical example. Let's say that we have a stack interface that looks like this. And by the way, I do need to make a brief aside here, since this is the first time we've written generified code in these lectures. We've used generified things, but not actually written them. There is a great deal to writing a generic class or interface, but all we need to understand for this simple example is that adding to an interface or a class name a bracket T, right, lets us use T as a type in its parameters and return lists. T will be filled in with whatever type we supply when we actually use the interface or class. The collection classes also supply a java.util.stack class. So would an object of this type work with code that expects our stack interface? Well, if we look at the Java docs, we can see the answer is close, but not quite. So, question 1, look over our stack interface, it's also in the transcript of course, and the java.util.stack class, and find 4 differences between our 4 methods and the corresponding methods of Java util stack. So, looking that over and getting an answer here then, first, our push returns the stack so that we can chain a series of push calls together, stack.push.push. The Java util stack has a push method that simply returns the item that was passed. not the stack. Now, a second difference is that our pop returns void, while the Java util stack pop returns the removed object. Third, we have empty versus isEmpty. They do the same thing, but they're differently named. And the same goes for top in our interface and for peak in the Java util stack. Now, to fix this, to allow code that expects our stack interface to work with a java.util.stack object, we create a stack adapter class right down here. Now, this class has a java.util.stack object as its only member, called libstack. And this is supplied to it via the constructor. Stack adapter implements our stack interface by calling corresponding methods on the java.util.stack, but adapting the calls appropriately. And note, by the way, we must use java.util.stack for the library stack class, since otherwise our stack class, which is in the same package as the stack adapter, would be assumed. The four method implementations are fairly straightforward. The adapter's push method calls the Java util stacks push, but then also returns this for chaining. The adapter's pop method calls Java util stack pop, but simply drops the return value. And the adapter's isEmpty and top methods call the corresponding but differently named methods in Java util stack. So, for instance, here's a simple main that tests the adapter and shows that it will work as expected. This code creates a stack adapter passing to it a java.util.stack. And it then works with the stack adapter STK as though it were a stack of our type, but it's actually working with the underlying java.util.stack with the adapter as a go-between. Now, this design approach works for any case where an older or third-party supplied class must be adapted to fit a slightly different interface. It's a classic design pattern, unsurprisingly called adapter in the Gang of Four text. It's also commonly called wrapper in industry, and I've even heard shim used to describe it. Now, typical UML for adapter is as shown in the diagram. We have a new interface and an old class that must be adapted to fit that new interface. And the go-between adapter class implements the new interface using a reference to the old class. Now, since we have a bit more time in this segment, and since we have the keys adapter object to play around with, let's look at one more design concept from the collection classes. So, question 2 here. Examine the Java docs for key set, and in particular, look at what they say about allowable operations on the set returned by key set. For instance, can I call clear on it? That's an allowed set method. Can I call add? Why are they different? And you will find they are different. Speculate on why that might be true. Why would they be different? So, returning from a pause where you've had a look at the Java doc, here is the documentation for key set, and the answer is that clear and remove and a number of other options that remove keys are permissible. But add, and add all for that matter, are not. Remember that a set like keys is actually operating on the underlying map. So anything you do to it, you're actually doing to the map. Removing key value pairs from the map is simple enough, but adding a new key also requires a corresponding value, and we can't supply that via add. So all we can supply is the key value. Now, one solution to this might be to define yet another interface, call it remove only set, that lacks an add method, and then have keySet return that as the adapter. But cases where a few methods are selectively disabled in an interface come up often enough in the collection classes that providing an interface for every such situation would result in chaos. Instead, the designers used an interesting approach, and one worth adding to your toolbox. Implementations of the standard interfaces, like set, are allowed to refuse to implement selected methods. And the documentation labels them as optional operations. The methods remain in the interface, so they can still be called, but they throw an exception if you do. And we can illustrate by uncommenting the add for keys and then running the thing. And what we will get is an unsupported operation exception. So there's no compile error, but when I run the code, I get that exception. Now, this is admittedly a bit of a hack, since it requires you to know that certain methods are off limits in certain cases, or you hit runtime, not compile time, bugs. It's as if the interface is saying, yeah, you can call all these methods, but be careful because some implementations will slap you if you do. Still, it's a fair compromise in cases where we want to disallow a method or two without creating a whole new interface. Now let's name this design pattern unsupported method and add it to the design patterns collection. Note, though, that this is a non-gang of 4 pattern, like the roster pattern from an earlier topic.